A very good morning to all of you. Today we are going to discuss uninformed search techniques, depth limited search and iterative deepening depth first search. First we will discuss depth limited search. So we have seen DFS, depth first search, in the previous session. So DFS can go infinitely deep in a search tree and may never return a solution, especially in infinite or very deep state spaces. In the case of depth limited search, it's a more modified version of depth first search and that imposes a maximum depth limit L. So here we can say that depth limited search DLS, that we can consider it as the combination of DFS plus depth restriction. So that means nodes beyond depth L are not expanded. So nodes at depth L are treated as leaf nodes. So that means we are not considering further nodes. So for example, imagine if we are searching for a book in a library, but you are allowed to check only up to the third floors. And even if more floors exist, you stop at floor 3. So we will see the algorithm. We have to start from the root node and explore nodes depth first, similar to DFS, and keep track of current depth. And if the current depth is equal to our limit, if we are setting a limit, if the current depth is equal to our limit, then we are stop expanding, and that will return if goal is found success. Then if limit reached, then it will return cutoff, and if there is no solution exists, then it will return failure. So we can consider if we have a current root node A and there are two children B and C. So first it will select B. Then B again has two child nodes D and E, and C also has child nodes F. Then we can see D has one more child, that is G. So if this is the structure, then here first it will expand A to B, then it will expand D. And if our depth limit is equal to 2, so that means our L is equal to 2, then what will happen? It will limit at level 2. So that means it will go through A to B, then D, and here D is not the goal state, then it will backtrack to B and check F, E, and it is not the goal state, then it will backtrack to B, then A, then go to C and check F. So if our depth is equal to 3, if instead of 2, if it is equal to 3, then nodes will be expanded A, B, E and G, and goal is found. So we can say that nodes at a depth limit are treated as dead ends or leaf nodes. So search does not go deeper. So here we can see an example. We are starting with the S. It is a root node and we are considering it as a level 0. This is level 0, and then we are considering level 1. That means it will move to A or B. So it will select A, level 1. Then level 2 we have C, D, I and J, and level 3 we have E, F, G, H. So if we are starting with the L is equal to our maximum depth limit is equal to 2 and the goal state is J. This is our goal state J. So what will happen is, and here it is 2 means up to level 2 only it will search. So we are not allowed to go beyond level 2. So we will see nodes at depth limits are treated as leaf nodes. So even if they have children. So here it will go from S to A and C. Then this is not the goal state. So it will backtrack to A and go to D. That is also not the goal state. So it will backtrack to S and go to B. Then I. It is also not the goal state. So backtrack to B. Then J. So goal state is reached. So here we can see that depth limit search can be terminated with two conditions of failure, that is standard failure value. It indicates the problem does not have any solution. That means if j did not exist in anywhere in the tree, then the algorithm would return a standard failure, meaning no solution exists. Next one is cutoff failure. Cutoff failure means the algorithm would return cutoff failure, meaning solution exists but not within the given depth limit. So here J is present in level 3, but not in this case. But I am telling if this is if our J is this, if this is J and this is something else, or this is H or something, then what will happen? We our limit is 2, so we won't search this level, so we will not get the goal state. So we can say that depth limit search is almost equal to DFS with a fixed depth limit, where nodes at the limits are treated as the leaf node. Then we will see the algorithm. Depth limited search is implemented using two functions. One is depth limited search. This is the one function, depth limited search. That is the driver function. Then we have a recursive DLS. So here you can see recursive DLS function. This is the actual recursive DFS with the depth limit. And here we can see that in this case, problem defines initial state, goal state and actions, and we have a depth limit, the maximum depth allowed, and we have a root node, and we are starting from the root node, and we have the function, the recursive DLS function, that's starting from the initial state. So here this recursive DLS function that actually performs depth first search but stops when depth limit is reached. That means that depth is equal to L. And if it is reached that level, it will not go further. So here we can see that if problem goal state, then not comma state, then return solution. So that means checks whether the current node is the goal. If yes, then return the solution path. Then search stops immediately. So goal state is always checked before depth limit. Then we can see else if limit is equal to 0 and return cut off. So that means limit is equal to 0 means maximum depth reached. So there node is treated as a leaf node, and search cannot be go deeper. They need to return cutoff. That means not. That means we reached the goal state, and till then we didn't get any goal state. Then here we can see cutoff occurred, then false. For each action in problem, actions not comma state. So here assumes that there is no cutoff initially. So initially we are setting it as false. Try each possible action. That means we will go through each children nodes. Then work exactly like DFS from left to right. And here you can see child node problem, problem, node and action. Result, recursive DLS, children problem, limit -1. So that means we are creating a child node and call the same function recursively and reduce the depth limit by 1. So depth decreases as the recursion goes deeper. Next, if result is equal to cutoff, then cutoff occurred true. Else, if result is not equal to failure, return result. So that means if any child node hits the depth limit, remember the cutoff occurred. And if a solution is found, immediately return it. And DFS behavior it is following. So then you can see if cutoff occurred. If cutoff occurred, return cutoff, and else return failure. So that means if any child was cut off, that means return, it will return cutoff. And if no solution and no cutoff, then return failure. And cutoff failure means solution may exist deeper, and standard failure means no solution exists. Then we will see the advantages and disadvantages. So we will first discuss the advantages. Memory efficient. Depth limited search returns very little memory because it stores only the nodes along the current path, similar to DFS. And it avoids the infinite paths by imposing a depth limit. DLS prevents the algorithm from going infinitely deep in an infinite search space. And then we will see the disadvantages. It is incomplete, so that means depth limit search is not complete if the solution exists beyond the given depth limit. So that means if L is equal to 2 and if our goal state is actually located in the third level, then we will not check the third level nodes. So in that case we will not get the solution. So that is, but actually the solution exists. So we can say that it is incomplete when when the solution exists beyond the given depth limit. And then not optimal. So if multiple solution exists, DLS may return a non-optimal solution as it does not guarantee the shallowest or least cost solution. And then choice of depth limit is critical. So if the depth limit is too small, then algorithm may miss the solution. And if it is too large, then it behaves like a DFS. And then completeness, depth limit search is complete only if the solution depth limit is less than equal to the depth limit. So that means if actually solution is present in the second level and our depth limit is 3, then anyway we will reach the solution. So in that case we can say that it is complete. And if the solution lies deeper than this L, then the algorithm return a cutoff failure. So then you can see time complexity. Time complexity that is actually b to the power L. So here we have b is the branching factor and L is the maximum depth. Then this is because the algorithm may expand all the nodes up to the depth L. And then we will see space complexity. Space complexity is actually big of B into L. Only the current path and the siblings nodes are stored in the memory. Then we can say optimality. Depth limited search is not optimal. Even if L is greater than D, it is not optimal. Since it's a special case of depth of a search, it does not guarantee finding the best or shallowest solution because we are not considering the cost here. Then depth limit search is a memory efficient depth of first search algorithm that avoids infinite paths by imposing a depth limit, but it is neither complete nor optimal in general. Next is iterative deepening depth first search. So this is a hybrid search algorithm that combines the advantages of DFS and BFS. So this algorithm repeatedly performs depth limit search, starting with a small depth limit and gradually increasing the depth limit until the goal node is found. So here we can say that initially the depth is set to 0 and then depth first search is performed up to this depth limit, and then if the goal is not found, then what will happen? The depth limit will be increased by 1. So this process is actually continuous until the goal node is discovered. So this ideas automatically determines the minimum depth at which the solution exists. So here it performs a series of depth first searches with the increasing depth limit. So here also it explores nodes level by level similar to BFS and uses a very little memory. So we can say that iterative deepening search combines the fast solution discovery of breadth first search with the memory efficiency of depth first search. So it is actually including the advantage of BFS and DFS by repeatedly applying depth limit search with an increasing depth limit. In this example, we can see that we are starting from the first node. So it is the root node and 11 is the goal node. and each level we will increase the depth limit. So initially we are setting depth limit is equal to 0, and there we have only one node, that is 1, this one. Then we are increasing our depth limit as 1. Then we have to explore 2 and 3. Then root and its immediate children are explored and goal state is not found, and increase the depth limit as 2. Then here we will check, 4, 5, 6 and 7 will be there actually. So the search goes deeper using DFS order. So that means nodes at depth 2 are treated as leaf nodes. So goal 11 is not there. So what it will do is it will search 1, 2, then 4, then it backtracks to 2 and it goes to 5, and 5 is not the goal state, so it will backtrack to 2, then backtrack to 1, then it will go to 3 right side of the tree, then 6 it is also leaf node, so it will go back and go to 7, that is also not the goal state. So what will do, it will increase the depth limit as 3. Now we have 1, 2, 4, 8. That is not the goal state. So go back. Then check 9. That is also not goal state. So backtracking 4, 2. It will go to 5. That is not goal state. Then 10. Then backtrack to 5 and go to 11. So goal state is reached. So here the ideas explores not level by level like BFS, and each iteration uses DFS with a depth limit. And nodes near the root are revisited, but the memory usage remains low. So the goal is found at the minimum depth ensures the optimality. Then we will see one more example. Here root node is A and the goal state is G, and here we are moving from left to right, and here we can see that at level 0 we have A, and level 1 we have A to B. It's not the goal state, so go back and A to C. Then it again increase the depth limit in 2, so it will go A, B, D, then backtracking to B, then E, then backtrack to B, A, then it goes to C, F, that is also not the goal state, so backtrack to C and go to G. Now reach the goal state. So the path is A, B, D, D, E, then go to C, F, G. So that is the final path. So here we at depth is equal to 0. We have only one node. Then there is node goal state. Then we will go to depth 1, then depth 2, depth 3. Like that, we will increase the depth until we reach the goal state. So nodes at lower levels are revisited. Then we will go to the next slide. That means we are discussing the properties of iterative deepening depth first search, that is IDDFS. So IDDFS is complete if the branching factor is finite. So this means that the algorithm is guaranteed to find a solution if one exists. Then time complexity means here we have the B is the branching factor and D is the depth of the shallowest goal node. Then here the time complexity will be B to the power big O of big O of B to the power D. So here nodes at upper levels are revisited. The overall time complexity remains comparable to breadth first search. Next, we will see space complexity. Space complexity will be big O of B into D. So that means IDDFS stores only the nodes along the current search path and their siblings, making it memory efficient. So it has the property of DFS. Then optimality, next property where IDDFS is optimal when the path cost is a non-decreasing function of the depth. So that means all the step costs are equal. Then in such cases, IDDFS always find the shallowest and least cost solution. And here we can say that IDDFS is complete for finite branching factor, has time complexity b to the power d and space complexity b into d, and is optimal when step costs are uniform. So iterating deepening search is an uninformed search algorithm that is particularly useful when the search space is large and the depth of the goal node is unknown. And here the algorithm repeatedly applies depth limited search starting with a small depth limit, and then it gradually increasing it until the goal node is reached. And we will see the advantages. It combines the benefits of BFS and DFS. That means it combines the completeness and optimality of BFS and memory efficiency of DFS. So we can say that it is memory efficient because it requires less memory than BFS as it stores only the current path. And it is complete because it is guaranteed to find a solution if one exists within the finite search space. And optimal, that means find the shallowest solution when all step costs are equal. Then we will see the disadvantages, and disadvantages, one main disadvantage is repeated work. So that means the main drawback of IDDFS is that it repeats the exploration of nodes in the earlier iteration, leading to the redundant computations. Then time overhead, that is another disadvantages. That is due to the repeated search, IDDFS may take slightly more time when compared to BFS in some cases. So we can say that iterative deepening depth of first search is an uninformed search algorithm suitable for all large search spaces with the unknown goal depth, and that is combining BFS completeness and DFS low memory usage, and but it has disadvantage is actually it has a repeated work. Okay. Thank you.